Oh, and I can see your
Yep.
slides.
Okay, that makes it nice and easy. So thanks for the introduction. I also want to call out that I've been working on this project with Yaru, Ben, Kyle, Tom Urim, also at Argonne. So it's been a big collaborative effort from start to finish. But let me talk a bit about this extreme scale survey simulation with Python workflows. And let me see if I'll actually switch slides. There you go. So I'm going to go pretty quick on this because I'm sure we're all getting very tired at this point. But just quick outline, I'm going to cover what the image simulation campaign even is, how we implemented Parcel as part of that, what sort of experiences we had during production and what lessons we learned, and how I'm basically going to be staring at FuncX longingly now that I know more about it. So quick version of this, LSST Desk is the Vera Rubin Observatory Legacy Survey of Space and Time Dark Energy Science Collaboration. It's a very long acronym. And we did the Data Challenge 2 image simulation campaign. Essentially, this observatory is taking the largest amount of data that the field of cosmology will ever have by photographing the entire night sky once every 3 nights. And we need to build scientific pipelines to test on data that's comparable to that, because honestly, we need to get systematic errors lower than we ever have before. And so the DC2 image simulation campaign is the most elaborate effort we've made on the front of simulating telescope quality images. It's a 300 square degree area of sky for 5 years of survey depth, covering multiple color bands, with both a wide, fast, deep field survey component, which is basically just the entire night sky every 3 nights that I was talking about, except for a small area of that. And a deep drilling field component, which covers transient objects like supernova, quasars, that sort of thing that you need to hit it many, many times over the year to get good science out of it. So what does the actual technical task look like in practice? So essentially, we have 30,000 individual telescope observations we call visits. And each of these visits consists of simulating the image on 189 distinct sensors of the camera, which are depicted as gray boxes on the figure to your right. Each individual sensor shares some information about a shared sky for a single pointing of the telescope, but must simulate the objects entirely individually for its own camera. And some object visits we come back to, and then we add all the transient stuff like supernovas and quasars that we need, but we simulate all the images with galaxies and stars and dust. And you can see what it looks like when we take 5 years of data and add it up and zoom it out so that you can actually see it. But that large inset square in just the sort of image we're trying to get out of this, and that small inset square is how much space it actually is on a single sensor. So we're just simulating a massive amount of data here. So how does this factor into Parcel? So IMSIM has a couple of, IMSIM's our image simulation code we use, has a couple of key inputs. It takes a catalog of objects to draw based on some very complicated decision tree, a list of sensors to simulate, and any checkpoint files from previous runs so that it can start over without going from scratch. And then what it does is it simulates all these objects. It simulates the intervening sky, so the dust from the Milky Way and our own atmosphere and everything that affects how the telescope, how the object on the camera will look different than if it was, just simulated without any of it. And it draws it into basically a telescope quality image. And that's our raw output, is just essentially an image that is identical to one you would get off the telescope itself. Parcel handles this by, we basically have a Parcel driver that runs on the compute resources itself in order to avoid some stuff I'll mention later. It starts up a bunch of workers on the compute nodes, runs pre-processing Python scripts to package our IMSIM tasks into small bundles that fit onto a single compute node. And then each executor that's on a compute node will then start up a Docker container. I use Docker in quotes because it's never actually really Docker. And then it will run our image simulation task inside the container. And as soon as one of those containers finishes, it closes out. Parcel puts in a new worker because we always have more work to do, basically. Just quick diagram to show how that looks like in picture. You have 189 sensors, 30,000 catalogs. So Parcel takes in that information. We run a Python script to divide it up into these bundles, which may contain sensors from different pointings of the telescope if necessary, though it does prefer to keep them all together. And then it executes these on either Theta or Cori, Theta being the ALCF resource, Cori being on NERSC. And then we generate black and white images that we then, stack all together to make our nice colored images. Our motivation behind using Parcel for this, just one major one, is that the code isn't really uniform in its necessities. So the plot to the right is a distribution of how long it takes to run a single sensor for just adding on deep drilling field objects. And so there's a pretty large time discrepancy here, about order of 10%. And that's driven by the fact that individual objects appearing on one sensor and not another can have vastly different runtimes because of this complicated decision tree. Objects much bigger, it might take a much longer time to draw because the Fourier transform is enormous, that sort of thing. This actually gets worse for the wide, fast, deep field, which has more objects to draw. In that case, the runtime of the actual simulation is actually around 10 hours. And the sensor, we still have this 10% effect. So you have like a couple hour leeway either direction for how long a sensor might take to run. And that's why we ultimately needed something like Parcel to be able to put tasks in and out as resources became available. So just quick production highlights. We were able to use 2,000 nodes simultaneously for this at Cori using KNL nodes, 2,800 nodes on Theta. And the workflow is actually configured that essentially we just have a few Python switches that we change, and it allows it to work quickly on either resource. We do still need to move around all the files. It's not perfectly cloud friendly, but we were able to make it so that things like, do we use Singularity or Shifter is essentially just a wrapper we change. I should note that we weren't really limited by Parcel in the number of nodes. We originally worked at 4,000 nodes for prototyping, but we had to scale down to queuing policy quirks that have since been fixed. And ultimately, we used 100 million compute hours to generate these images. So quick lessons learned. I mentioned that we ran Parcel on compute nodes, and that was because we had an issue where the running Parcel on a login or a head node essentially ran into an issue where it would sometimes be restarted for some reason or another. Parcel would stop. And then if the job started out, the compute nodes would hang around doing nothing, and it was all very sad. So what we ended up doing in our quick case was running it on the compute nodes, but a better possibility is to look into remote-driven workflows. We had been considering previously something running on AWS, but it looks like FunkX handles a lot of the same things that we were interested in back then, as well as other projects discussed. It seems to be a very active field of interest. I'm also noticing that workflow nodes are starting to become popular on NERSC and ALCF, and so we were looking into exploring running Parcel as a long-term running process on these, so it doesn't get in the way of things on the login nodes or potentially get restarted as much as login nodes sometimes do. Further containerization studies is interesting to us. We want to know how much time we lost or gained by using containers. We obviously gain in portability, but it's potential that the Python that was built inside of the container is less effective than a Python that would have been specifically built for the machine architecture. So we didn't explore that at the time, but we want to in the future. Unfortunately, we don't gain some of the containerization benefits, like loading of Python libraries being faster. I mean, technically we gain it, but when our code runs 10 hours, that's sort of a moot point if it took 10 minutes to load the Python library or 12. And finally, now that we've run this first project, we can think more of how to improve the code itself toward parallelization. So our downside to containers is we can't put new work into the container in this workflow. It's potential another workflow will be set up in such a way that we can just pass things in and out of the container. And also we can just minimize lost time in the container or work around it in some way. Currently, the IMSIN team is looking into restructuring their code so that rather than parallelizing over sensors for a single pointing of the telescope, you instead just simulate one sensor on a compute node and have your parallel threads each drawing different objects on the camera, which in some ways is more realistic because the light doesn't line up in an orderly queue to be collected by the telescope. So quick conclusions. This is the largest survey simulation of its type and complexity, so it's a really unique effort. The workflow itself is entirely Python driven, which is fantastic because I understand Python and a lot of people find it a lot easier to understand. Our containerization is pretty flexible thanks to Singularity, Shifter, all essentially providing you the ability to pass it a Docker container and they rebuild it as whatever container version they need. And the workflow itself is very flexible, and we're looking to doing more with it in LSST Desk in the future. You heard Ben talking about how Parcel is being used for image processing, for example, but I'm also looking into using Parcel for developing a scientific pipeline inside of LSST Desk as well. So future's looking great for Vera Rubin, and hopefully we'll get to leverage Parcel a lot more going forward. Okay, I think I talked too fast, but I have no clue what my time was. So if there's any questions?
No, that's perfect.
Oh,
yeah, I think we've got time for one quick question. Okay, I will ask the question. So I saw you are currently running on Cori and Fader. Is there any benefit to running on both of them concurrently, or is it a task that you could just split up sequentially, essentially?
So in our case, a lot of this, the data actually is rather trivially parallelizable. So we could potentially have set up the workflow so that we could run simultaneously on both resources, just passing it different subsets of the data. In our case, we didn't do that because there was a little bit of suspicion about how much things, what's the word? Reproducible at the machine level. We were a little worried about that, and testing that did slow things down. Also, just queuing or reservation. No, allocation is the word I'm looking for. Allocation politics factored into things a little bit. Namely, we were running out of time to use our NERSC allocation, so we used up all the NERSC allocation, and then we had to use up all the theta allocation.
Okay, that makes
but in
sense.
the future, I think we're really interested in trying to see if we can leverage multiple resources simultaneously.